Hello friends, welcome to lecture number 5 of gamma beta function of mathematical physics. And here we're going to discuss about the definition of beta function, properties of beta function, a relation between gamma and beta function. Okay, so we have already discussed about gamma functions, and I have solved many problems of gamma function in previous lectures from lecture 1 to 4. So please watch all the lectures for better understanding. Okay, so links are given in the description box. And before we start, please subscribe the channel if you are new to my channel. Also share with your friends, stay connected, and also hit the bell icon so that you get notified when new video will be uploaded. You will get notified. Okay, so now let's start. So what is beta function? Now you see beta of L comma m, that is equal to 0 to infinity x to the power L minus 1 into 1 minus x whole to the power m minus 1, right? Dx is called beta function, is called beta function, is called beta function. And how to evaluate a beta function? Okay, so how to evaluate a beta function? Evaluation of beta function of L comma m. In order to evaluate this, we can take the help of gamma function, that is gamma of L gamma m by gamma L plus m. Okay, so let us prove this relation first between the gamma function and beta function. There are two ways to prove. First one, we're going to prove, we're going to start from this definition of beta function, and the next process is you can do from the you can start from the definition of gamma function. Okay, so first let us start from the definition of beta function, because in order to prove using the definition of gamma function from the right hand side, we must know some properties of beta functions which are not discussed yet. So let us discuss first let us prove this relation from this left hand side. Okay, so now let me go to the next slide in order to prove this relation between the gamma function and beta function. So here you see, let us prove this. Okay, proof. So now you see, first we know that just wait, let me little bit of arrangement here in order to find space. Okay, so here you can see that we know the definition of beta function. We have already discussed that beta of L comma m is given by 0 to 1 integration x to the power minus x to the power L minus 1 into 1 minus x whole to the power m minus 1 dx, right? Now let us integrate using integrating by parts. So we're going to take this one as first function, because it will be easier to this property that integration of u v dv dx is equal to u integration of v dx minus integration ddx of u, then integration v dv dv, right? This property. So here you can see, if you take v as x to the power L minus 1, then it will be easier to integrate. So that's why we can take this one as first function. Okay, so now beta L comma m integration 0 to infinity, not infinity, 0 to 1 minus x m minus 1 x L minus 1 dx. Now let us take this one as u and this one as v, then use this property integrating by parts, right? So if you do so, then what you're gonna have, that beta of L comma m, first function is taken outside of the integral minus 1 whole to the power minus 1, then integration of x to the power L minus 1 dx, that's going to be equal to x to the power L minus 1 plus 1 divided by L minus 1 plus 1, right? So here we have applied this formula x to the power n dx. We know that x to the power n plus 1 by n plus 1, right? So using that identical formula, here we have got that x to by L, it should be x to the power L. So yeah, integrating this, we have got x to the power L by L. So let me write here x to the power L by L, right? We are integrating it from 0 to 1. Now let me clean this part. Just wait. Let me write it properly. X to the power L by L. Now you see. Now let me go to this part here. Minus 0 to 1. Then you have to take the derivative of u, that is u dash. U dash means du by dx, right? So here u is taken as this, right? What we have taken, 1 minus x whole to the power m minus 1. This is taken as u. If you differentiate it, so here it is not only x, it is function of function. If you differentiate it considering x to the power n, if you differentiate it, you should get n into x to the power n minus 1. According to that, m minus 1 x, sorry, 1 minus x whole to the power m minus 1, that is m minus 2. As this is function of function, this is not simply x. So again you have to differentiate, you know, this 1 minus x, right? So if you differentiate 1 minus x, then you're going to have minus 1. So here we're going to have minus, right? So that is what we have got. This minus, it's going to be plus, right? So that's why it's going to be plus. So let me write these things here. Just wait. Let me first clean this thing. Just wait. Okay. So this is what we have got, u dash. This part is u dash. Now again you have to find integral of v, right? V is taken as this, and we have already got the integration of x to the power L minus 1, that is x to the power L by L. So here I'm going to write x to the power L by L simply, so dx, right? So hope you have understood this. Now you see, if you put here 1, this term going to be 0, and 0 into anything is 0, so this term will be 0. And if you put 0 here, if you put 0, then you're going to have 1, and if you put 0 here, then it's going to be 0. 0 to the power anything is 0, 0 into anything is 0. So finally this term will be again 0 for upper and lower limit both. So here we're going to have 0 minus 0, that means simply 0. So our results become 0 plus, again here you see these things are constant, so can be taken outside. So m minus 1 by L integration 0 to 1 minus x whole to the power m minus 2, then x to the power L dx, right? Again taking this one as v, taking this one as v and this one as u. If you apply again integrating by parts, so let me write these things. Let me go to the next slide. Okay, let me copy this result b of L comma m. Let me copy these things and let me go to the new slide. Okay, so here is the new slide, and here you can see, so this is the result we have got. So now again if you see, again if you integrate using integrating by parts, then what you're going to have, so then you will have m minus 1 by L, then u is taken outside, 1 minus x whole to the power m minus 2, right? So then if you integrate x to the power L, if you integrate x to the power L dx, right, then you should get x to the power L plus 1 by L plus 1, right? So you should get x to the power L plus 1 by L plus 1, right, 0 to 1, right? So again here you see, just then you have minus integration of derivative of this, that gonna be m minus 2, then derivative of 1 minus x, this if you differentiate this, then you should get m minus 3 here, x to the x minus 1 minus x whole to the power minus 3. And if you differentiate it again function of function, then you're gonna have a minus 1, so that's gonna make this plus, and again we're gonna get this term. So x to the power l plus 1 by l plus 1. And just wait, let me use here curly bracket, and here we're going to use square bracket. Right now, again, if you put 0 and 1 for both the upper and lower limits, this term going to be 0. Okay, this term going to be 0, and we're going to left up with only this term. Right, so just wait, here we should use the square bracket, here we should have closed up this one, square bracket. Okay, so here we're going to have m minus 1 by l, then from here we're going to have m minus 2 by l plus 1, m minus 2 by l plus 1. Then you see we will have 0 to 1, 1 minus x, m minus 3, x to the power l plus 1 by l plus 1 dx. And if you observe all the three steps here, you can see b, l comma m. So what we have got here, you can see that let me show you something. Let me copy this result first. Okay, just wait. So here is the result. I don't think I need to copy it again. So first we had this first step. You can see if you compare this step, all these three steps, this one here, you can see this part, and if you compare this one, right, if you compare the results and this one, right, so then what you will get, what you have observed. So first let me copy these things. So just copy it. Let me go to the new slide. This was the first step, right? So I missed the dx here, right? So next one is this. So this is the next one, right? Copy this and paste here, right? Let me copy this. You don't need to repeat this all steps, just for to analyze this three steps I have taken in one slide. Okay, so here you can see, so once you have integrated this, you have got here, let me clean these things, let me ignore the 0. So you have got here m minus 1 by l, and here you have got m minus 2, and here you have got l. That means this power is increased by 1, right? So and this power is increased by 1, and here this is reduced by 1, right? This is reduced by 1, and you can see that here we have got m minus 1, sorry, here we have got m minus 1 by l. Now we are getting m minus 1 by l, then m minus 2 by l plus 1. So this is increasing by 1, and this is decreasing, it is reduced by 1, and here again this power is also reduced by 1, and this power is increased by 1, right? And if you continue using if you continue this integration by integrating by parts, then you're gonna have next step, you're gonna have l comma m, beta function of l comma m, you're gonna have m minus 1 into m minus 2, then you're gonna have m minus 3 divided by l into l plus 1 into l plus 2, right, and so on. Then integration 0 to 1. So here you're gonna have, instead of m minus 3, now you're gonna have 1 minus x whole to the power m minus 4. Then you're gonna have x to the power, this is l plus 1, instead of that you're gonna have l plus 2, and this L plus 2 is taken outside here, right? You can see that. So that's why, so we're going to write this one x this. So sorry, it should not be written twice. This is written already here. Okay, so this is L plus 1, right? So that is what we're going to have. Now you see, so just let me delete these things, right? Just cut it off. Now let me go to this step. Here you can see. So what was the previous step? This was after this we have got this result, and if you continue so on, then next step will be your m minus 1 and m minus 2 and m minus 3. Then you're gonna have m minus 4 and so on, dot 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 2 into just wait, next step will be this one, and here you will get L plus 1, L plus 2, L plus 3, right? And next 0 to 1, so here we're gonna have 1 minus x, m to the power minus 5, then x to the power L plus 3 dx, right? We're gonna get this one. So if you see, if you observe the pattern, if you continue this way, you're gonna have you're gonna get such a stage. At one stage you can have m minus 1 into m minus 2 and into m minus 3 dot 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 2 into 1, so on, right? And here you see this, you can see this is m minus 5, so you can write here this, instead of 3 you can assume this one as 5 minus 3, right? Sorry, 5 minus 2. And here you can see this is m minus 4. You can consider this 2 as 4 minus 2, right? Similarly, if you continue this step, then what you will get, 0 to 1, then 1 minus x, m minus m, and x to the power L plus, here instead of 5 we have m, so we're gonna write, when there was 5 we had written 5 minus 2, so here we're gonna write m minus 2 dx. Now you see here x plus 3, so here is also x plus 3. Now we have this, so here we're gonna have L plus 1, L plus 2 dot 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 dot, and it's gonna end up with L plus m minus 2, right? And this thing's gonna be 0, and anything to the power 0 is 1, so we can cut it, right? So here we're gonna have this result. Now let us integrate this. So just wait, let me erase these things. So if you integrate this, then what you can have, just wait. So we have continued this. So now m minus 1, m minus 2 dot 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 2 into 1 divided by L into L plus 1, L plus 2 dot 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 L plus m minus 2, and if you integrate this, then you're gonna have x to the power L plus m minus 2 plus 1, then x L plus m minus 2 plus 1, so which makes it minus 1, and here also it's gonna be minus 1, so we can write this one with this, right? So we have got this result. So let me write this write these things here. So you're gonna write this here. So here we have upper and lower limits, so 0 to 1. Okay, so when you will put 0 here, 1, then 1 to the power you're gonna have L plus m minus 1, so that's going to be equal to 1. 1 to the power anything is 1, and when you will when you will put 0, then you will get 0. So 1 minus 0 is again 1, so this thing is going to be equal to 1, right? So that's why our final expression will be something like this. Let me clean these things. Okay, just wait. So let me copy these things and let me go to the next slide. Okay, so now let me copy this. Okay, here is the new slide. So here beta function of L comma M, that's gonna be M minus 1 M minus 2 dot 2 into 1, here L into L plus 1 L plus 2 dot L plus M minus 2 L plus M minus 1, and here it is 1. So 1 into anything is that thing, so just keep it like this way. So here you can see this thing can be written as M minus 1 factorial, right, if I am not wrong. And here you see we have L plus 1 into L plus 2 dot and L plus M minus 2, and this is L plus M minus 1. And similarly, if we continue, then next step we can write here you see, let me to make it to write it in factorial form, we have to continue up to this step 2 into 1, right, 3 into 2 into 1. So that's why what we're going to do, we're going to multiply here and here. What are the next terms going to be? That's going to be here you see, wait, let me write these things in reverse order, because here you see, so these terms are going decreasing from this side to that side. Here L plus 2 L plus 1 and L, this is, and next time here we're going to have L minus 1 and then L minus 2 and going to 2 into 1 this way, right? So that's why let me write the denominator in reverse order. Just wait, just wait, give me a moment please. Right, okay, so we're gonna write L plus M minus 1, then L plus M minus 2, just wait, minus 2 and dot here we're gonna have L plus 2 L plus 1 L, then we're gonna multiply L minus 1 L minus 2 dot 2 dot 1. So this part is multiplied here with the denominator, then it must be multiplied with the numerator as well. So here you see, this part we can write, this part from here to there we can write factorial L, right, we can write factorial L. So in this denominator here already up to L, so now consider these things, we have to multiply these things with the numerator as well as we have multiplied in the denominator, 2 dot 1, right? So here you can see that M minus 1 factorial, M minus 1 factorial, and these things can be written as, these things, this part can be written as N minus 1 factorial, right, N minus 1 factorial. So let me write here N minus 1 factorial divided by, and this whole series can be written as, this whole thing can be written as L plus M minus 1 factorial, right? So this is what we have got, beta of L comma M. Now let me copy this thing. Let me go to the next slide. Here you see, just wait. So here you can see that, let me clean this thing. So we know that gamma of n plus 1 is factorial n, right? So gamma of n plus 1 is factorial n. So if we have factorial m minus 1, that must be gamma of factorial m minus 1 plus 1, that means gamma m, that is our factorial m minus 1, right? Similarly, factorial n minus 1 is gamma n, and factorial L plus m minus 1, this is going to be gamma L plus m, right? So we will get gamma m gamma L by gamma L plus m minus 1, not m minus 1, L plus m. So this is what we have got. This is the relation between the gamma and beta function, and using this relation we can evaluate beta functions, value of beta functions. So this is proved, and we can use another method to prove this relation. We're going to show it later, but here you see. So before that we must know some property of beta function. So property 1, that is property of beta function. That is what beta of L comma m is also equal to beta of m comma L. Now let me prove this one as well. Okay, now let me copy this. Let me go to the next slide. Here we're going to prove this, right? So let me show you how to prove this. Now here you see, this is the proof. Just let me write it clearly. Proof. So here you see, by definition of beta function, beta of L comma m, that's going to be equal to 0 to 1 x to the power L minus 1 minus x to the power m minus 1 dx. That's what we know. Now we have a property. Now since if you use this property of integral, that 0 to a f of x dx, sorry, not dx, yes, dx is equal to integration 0 to a, we can write f of a minus x dx, right? And if you use this property, then we can write this beta function this way: beta of L comma m integration, here we have, instead of a we have 1, so that's why this is going to be 1 minus x, right? So in that case, this x is going to be 1 minus x whole to the power L minus 1, and this is going to be 1 minus x, and if you remove the bracket, then it's going to be 1 plus x, right, whole to the power m minus 1 dx. That is what we're going to have. Then this one cancel, so we can write this simply x to the power this, right, x to the power m minus 1, right? So now you see, if you compare this one, this is, now we have, when we had x to the power L minus 1 and 1 minus x to the power m minus 1, then we used to write beta L of m. Now this powers are interchanged. Here you can see this is m minus 1 on x, but in this case on x the power is L minus 1, right? So simply we can say, now we can write this as 0 to 1 x to the power m minus 1 and 1 minus x to the power L minus 1 dx. Now here you can see, if you compare this, when we had here L and here m, we had written beta L comma m. Now instead of L we have m, and in place of m we had L, so we can write this as beta of m comma L, right? Hence it is proved. So hope you have understood this. This is one property, and now let us discuss about transformation of the beta function. So we have already got this by definition of beta function, beta of L comma m. According to the definition, we have already got 0 to 1 and x to the power L minus 1 minus x whole to the power m minus 1 dx. We have got this form. There is another form, that is 0 to infinity x to the power L minus 1 and by 1 plus x whole to the power m plus 1, right, m plus 1 dx. That is another form, right? Sorry, this is m plus L, not 1. This is m plus L, or you can write L plus m. right? So let me show you this. So let me prove this. Here you can see that we know that beta function, beta of L comma m is defined as 0 to 1 x to the power L minus 1 1 minus x to the power m minus 1 dx. Now let us substitute now let us let us put that x is equal to 1 by 1 plus y. So if you differentiate it, if you differentiate dx by dy, then what you will get? If you differentiate this, then you're gonna have minus 1 by 1 plus y square, which implies that dx is equal to minus 1 by 1 plus y whole square dy. That is what we used to get. This should be dy, right? And this implies 1 minus x, and that's going to be 1 minus 1 by 1 plus y, and 1 minus x, that's going to be 1 plus y into 1 plus y minus 1, which is equal to y by 1 plus y, right? That is what we have got, 1 minus x, right? So let us use these values, this one here, and let us use this value of dx here, and let us use this value of x here. Okay, then what we're gonna have, let me clean these things. Okay, just wait. Then in that case, beta of L comma m will be transformed to this infinity. Why infinity? I will explain this. Just first let me write this. Sorry, the infinity to 0. How we have got infinity to 0? I'm gonna explain this. So first let me substitute here. X is replaced by 1 by 1 plus y whole to the power L minus 1, right? Then 1 minus x is replaced by y by 1 plus y whole to the power m minus 1, and dx is replaced by minus 1 by 1 plus y whole square dy, right? That is what we have got. Just wait, let me write this thing here, minus, let me adjust these things. Okay, 1 by 1 plus y whole square, then dy. That is what we have got. Okay, now you see there is minus. If you make it positive, then you can change it to 0 to infinity, right? So hope you know this property, right? If you have a to b f of x dx, then you can write minus b to a f of x dx, right? So this minus and this minus will be plus, right? So hope you have understood this. Just clean this thing. Okay, right? So what we have got now, simplify all this, then you will get y to the power m minus 1, and in the denominator here you're gonna have 1 plus y whole to the power 1 plus y whole to the power L minus 1, and here we're gonna have m minus 1 plus m minus 1, then here we have square, so plus 2, minus 1 plus 2 gone, so we have L plus m simply. So here we're gonna write simply L plus m, right? This is L plus m dy. That is what we have got. Okay, so now what we're gonna do, just replacing y by x. Okay, so let me write the last step. Let me write this last step. Let me copy this and let me go to the new slide. So here is the new slide, then the last result we have got this, and let me copy these things as well. So if we replace just wait. So if we replaced y by x, then this result's gonna be L comma m 0 to alpha x, then y is replaced by x now, so x to the power m minus 1 by 1 plus x whole to the power l plus m, or you can say m plus l dx. Okay, so this is the result we have got, right? So hope you have understood this. Now let us explain how I have got here infinity and here 0 when there was 0 to 1. Now you see, as you have considered here x is equal to 1 by 1 plus y, so here you see x is equal to 1 plus y. Now you see, this is now function of y, this is now function of y. So if you put y is equal to infinity here, if you put infinity here, 1 plus infinity, again infinity, 1 by infinity, it's gonna be 0. So there was 0, right? Now you see, then what if you put 0 here, if you put y is equal to 0, then it's gonna be 1 by 1, then x will be 1. So here it is 1. So that is why this 0 to 1, this limit 0 to 1 becomes infinity to 1. So hope you have understood these things. Now in the next video that gonna appear at the end of at the end of this video, at the end screen, you can continue watching this video and click the thumbnail of the next video that gonna appear at the end. So there we're gonna prove this relation using the definition of gamma function, right? So that is the relation between beta and gamma function. Now let's move on to the next video. Okay, next part, lecture 6.